how many think you can draw this?
I can do the second half.
Yeah, the 2R, 3S, 4S is kind of hard.
Alright, I'll make it easy. I'll start the Fischer projection for us.
Thank you. Is this on the test?
So you would draw a Fischer projection for this?
So how many asymmetric carbons do we have?
3.
Yeah, we have 3. 1, 2, 3, and I have 3 of these there, and so now we can, this is how we number the chain. We come to a substituent at carbon number 2. There's one at 3 and one at 4. So here's an idea. Let's just put in the substituents and then see if how close we get. How about that? Gotta have a 2-chloral, so that's presumably a hydrogen, 3-methyl, and then a bromine, and then let's just pretend we had to name this. So now I'm going to give this first priority, this fourth priority. I'm looking at things bonded to this carbon. Now I'm going to get rid of our numbering of the chain now that we got that figured out. So this carbon has a hydrogen, a methyl group, a chlorine, and this thing here. What do you think I should give number 2 priority? Which has a greater priority, this carbon or that carbon? Yeah, the top one. This carbon has 3 hydrogens attached. This carbon has a bromide, a carbon, and a carbon. If we made the list of what was attached, I'd get 3 hydrogens on this carbon, and on this carbon I would get a bromine, a carbon, and a carbon. I don't want to muck that all up, so I'm going to put a 1, 2, and 3. And so if I go 1, 2, 3, looks like I'm turning the car to the left, but my lowest priority group is going out at me, so it should be R. I can test that out with my right hand. If it doesn't get too awkward, the hydrogen's going out. It won't be awkward now. Hydrogen's pointing out, and I go chlorine, that carbon, to the methyl group. So I'm going to call that one R. Chlorine, backbone of the chain, and to the methyl.
It's R.
This is my right hand. And of course, when I stand here and do this, 1, 2, 3, I'm going like that. So it looks S, but hydrogen's coming out at me. Yeah. So if I take my right hand, put it coming out, because hydrogen's coming out at me, and I go chlorine, the carbon backbone that has a bromine and a methyl on it, and then to the methyl. 1, 2, 3. Those are my priority. Alright, so moving right along, let's erase this. So this asymmetric carbon here, what's going to be number 1? What's going to be number 4? Alright, now, who is number 2 and who is number 3? I call that number 2 because I have a bromine, a carbon, and a hydrogen. Down here I have, so this carbon has a bromine, a carbon, and a hydrogen. This one has a chlorine, a carbon, and a hydrogen. So this is going to be number 3. That one's number 2, number 3, and number 4. So now if I go 1, 2, 3, looks like I'm going around like that. I got a 1, a 2, and a 3. But my lowest priority group is what? Coming out at me. This thing's coming out at me. So looks R should be S. I could try my right hand rule, and look, I'm going to go 1 to 3, and then the 2. So I think my left hand is what I want to use here. Got my thumb pointing out, because the methyl group is pointing out. I'm going to go bromine, that carbon, down to that carbon.
So it's S.
So I'm going to call this S. Here, looks R.
So I'm just going to go 1.
Alright, one last asymmetric carbon to figure out. Highest priority group is the bromine. Lowest is the hydrogen. Which one's number 2? Which one's number 3? Yeah, that's got to be number 2. That's number 3. 1, 2, 3, looks are. Turning the steering wheel to the right, but the low priority group's pointing at me, so I'm thinking it's S, right? 1, 2, R. I'm gonna say S. So now let me test it out. I'm gonna take my left hand, this hydrogen's coming out, and I come over here and I go bromine, carbon backbone, and then up around to this thing. Bromine, carbon chain, bromine, carbon chain, top of the... Now that we got that figured out, let's name this. Well, we have 2R, look out, 2R, 3S, 4S, 2 chloral, 3, 4, di. Does Alex give you any of those to practice? So we all need more practice thinking about some of these things. First thing I would want to do is figure out what type of substrate we have. And this is a secondary alkyl halide. And the next thing I'd want to figure out is what is the nucleophile. And while you're thinking about what the nucleophile is, I'm going to cue up. Sodium is the nucleophile. What do you suppose the nucleophile is?
Sodium.
What's the charge on sodium?
-1. Wait, no. +1.
So it's an electrophile, but it's the counter ion to the nucleophile. Here is, if you ever see my mouse and I'm talking, say nobody can see that. So here is the nucleophile. I would put this on my card.
The scale?
I mean, that could take up.
You can write pretty small. You know how that
Is it front and back or just one side?
it's from that.
All 6 sides.
All 6. Do it.
Strong nuke. So what does that mean? Secondary alkyl halide with strong nuke equals Sn2. So what that means is I'm going to do a substitution, and chlorine's going to be the leaving group, and I'm going to replace that with iodide. Here I see it replaced. Here I see it replaced. What do you also know about Sn2 reactions? Inversion of our asymmetric carbon. So that means I'm thinking it's only going to be that one. Now, what about this red herring here? Equal amounts of 1 and 2. That's what we'd get if we had an Sn1, and where we get racemerization. Answer B. So I'm thinking on the last quiz I gave, if you had this in front of you, you want to put sodium iodide on a Fischer projection or whatever. So nucleophiles get substituted in. So here's a nucleophile, kicks off X, makes an alkyl halide. Here would be something like sodium hydroxide, and you wouldn't want to put sodium anywhere near this thing. Make the alcohol. Here's an alkoxide, make an ether. So I think practically all of these here are strong nucleophiles. Looks like we really don't have any weak nucleophiles on this page. Well, we have a moderate. Look at this one here. That's right there. But we can follow these halogens. By analyzing the starting material and the products, the following reaction is an example of what type. Begins with the letter S. Close? Why do we know it's Sn2? Well, yeah, I could say draw an energy diagram for that. That's an awful looking energy diagram. Didn't leave any room for my reactants. My favorite topic, stereochemistry. What's going on with the stereochemistry? It's on the opposite side. So this has got to be Sn2 because the inversion of that stereo center. And for fun, what do we think the nucleophile might be? Thought I saw it here. This thing here, azide. That'd be that thing there. Inversion of the stereo center. We see a bromine here. We see a N3 here. That means something got substituted. Divide the major organic products, which will result in the reaction below. So the first thing I want to do is figure out what type of alkyl halide do I have. It is secondary. What type of nuke do I have? Alright, so memorize for a second this part of this chart. I'm going to make it go away. So I have a weak. So when we have a secondary substrate, weak nucleophile, mainly the weak nucleophile, we've only thus far studied one thing, and that is the substitution. So if it's weak, it's going to be like that. So we might say, well, man, how do I know what we're going to form? All right, we know what they are. Since this is Sn1, the leaving group leaves, and then I'm going to have something that looks like this. Now I can do a little better drawing, perhaps. And there's the formation of a carbocation. This is the rate determining step. Now this alcohol will attack, and then another alcohol will come by. So notice it says products, where we have inversion of the stereocenter. And that's why on this problem here, they said, oh, maybe you have an Sn1 reaction, but you don't have that because it's Sn2, because the nucleophile was strong. But this one here, where you have a weak nucleophile, you have an Sn1 reaction, the leaving group leaves, and this carbocation is flat and planar, and the nucleophile can attack from the front side or the back side, giving you two different isomers here. And for fun, what type of isomers are these? Distereomers, or are they enantiomers? They're distereomers because one's not the mirror image of the other. We could call this one trans and this one cis. Typically the cis-trans isomerism is for distereomers. You don't have this mechanism on your exam tomorrow, but this will be good for the final and probably chapter 7, because all the Sn1, Sn2, and E1 and E2 are all possibilities. And so I'm going to say this is a weak nuke and secondary alkyl halide. So I'm going to say this is going to be an Sn1 event. Leaving group leaves. Now I'm going to take some license to say here is a hydrogen. And what type of carbocation do we have here? Secondary carbocation. So I'm going to draw this and say that we have a hydride shift. Now I have a tertiary carbocation. Then this nucleophile can attack. Then some solvent can act as a base. Pull that off. Any question? Probably a week from Friday you can see a quiz that would have a carbocation rearrangement.